Welcome to the world of geometrifying trigonometry. Geometrifying trigonometry is sometimes called as geometrization of trigonometry. Geometrization is an important subject in any kind of semantic analysis and for topological verification of the systems, because for long time, near around in last 3000 years, the trigonometry was there to measure the lands, to do the surveying problems, and several issues were there from the time of antiquity to handle the geometric problems, to measure the geo, that is to measure the earth. But trigonometry became a shortcut, and after 1590, trigonometry turned into the algebra-like object. It started to become algebra-like object after Ptolemy, but it took time, and when it took the form of algebra-like object, people were not very much happy to do geometry way of handling trigonometry, because drawing is a tough art. It is not easy. Moreover, drawing things with ruler and compass is also not easy. Euclidean geometry is very intuitive, very visual, very logical, but a problem is Euclidean geometry is too much non-commutative but associative. You have to have a deep intuition, you have to have a very good sense of understanding of shapes, the locations, positions, translations, rotations, scaling is very necessary to get a grasp on all of these things. To understand the axioms of Euclidean geometry and to keep the theorems of Euclidean geometry in mind is not very easy for students. So handling trigonometry with pure geometry was not very easy for many people for a long time. And algebra is like following some rules just as a rule of thumb, and following some rules give you some numerical answers that gives comfort to a large segment of peoples, but that don't generate intuitions too much. After 1900, algebra is dramatically changed after David Hilbert's 23 problems, and after Amy Noether, there came the new kind of algebraic understanding with the groups, rings, fields, and structures came into the play. The structuralism, the post-structuralism, and the way of automated calculations, automated theorem generation, automated theorem finding, automated deep insight generation became the new motive for algebra analysis, and algebraic structures took place in every stages of computation. Then computer science came and several things became easy, many things became computable, and geometry is also in a high area of research under computational geometry. Then human being again found it very interesting because mental stress reduced to calculate many things. Now again after 1990, when artificial intelligence and CAD systems, computer-aided design systems, became matured enough, then people were again becoming interested to get deeper insights into geometry, such that we can do topological analysis, such that we can do more optimized calculations with topology, and new adventures were started to do the computational quantum mechanics. Quantum logic also came into the play, and people became more aware with the understanding that the four states are taking very important role in new kind of analysis with quantum computations and possibilities of quantum computing are also taking places. So newer kind of deep insights are necessary. Now, after the topology became a important subject from Poincare's time, and then after Einsteinian way of space-time calculations, then due to the EPR paradox and due to new advents of research on genetics, then protein folding, and also the researches on symmetry, the behaviors of translation, behaviors of rotation, behaviors of flipping, behaviors of mirroring, behaviors of scaling are also taking into place, and human beings are getting more interested to get into the subjects with non-commutative behaviors with multiple symmetry options are also researched. But still, the trigonometry expressions were not geometrified, that is, geometrifying trigonometry or geometrizing trigonometry. In the academic world, it is well known as geometrization. The term is from the geometrization conjectures of Thurston, and geometrization is important because after we can do geometrization, we can do topology mining, we can do data mining, and until the things are geometrized, we cannot get more number of data, and until we get more number of data, we cannot do data mining, we cannot do pattern recognition, we cannot do more theorem finding, we cannot do more identity searching, we cannot do more kinds of equivalence checks. And after 2013, when homotopy type theory came into the play, we are now more interested to search for multiple layers of equality. The equality are also not of same type, there are multiple levels of equality now, and we can categorize the different kind of equivalence classes, deeper equality, the swallow equality, semi-swallow equality. These kind of equality checks are now very important in our logical designs, and mostly in quantum computations also these things will play a big role. When we think about any algebra, we try to search a closure principle. Suppose we should have a set of objects, and then within that set of objects we find some operation, and when there is any operator which would like plus, minus, into, divide, these are operators of arithmetic, and whenever there are operators, first we try to check is it following the rule of closure. What does that mean? Suppose the elements of the set S is taken and plus, minus, into, divide are done on that. When two elements are taken from a single set and the third element is formed due to these operators, this third element should also become a member of the set which we are considering. Suppose if S is a set of objects, then if A, B, C are three kind of elements of that set, then A plus B should become a C, then C should A, B, C all should be the element of the same set. Whenever we are trying to do the logical analysis with algebra like things, then we should first check that they are following a closure principle or not. In trigonometry, the functional objects which interact with each other are line segments. We cannot interact the objects with non-line segments. Circles are not the good things to interact. Points are not mature enough as the structural and functional objects in geometrifying trigonometry to interact with each other. The most fundamental structural unit of geometrifying trigonometry is the line segment, and line segment are of having four symmetries, because line segment has a vector like property, but both side vectors are allowed. Suppose O and P are the two endpoints of a line segment, then every line segment has a start point and end point. Suppose we can think O as the start point and P as the end point with a left hand side, and we can think a right hand side of the vector. So a line segment can be thought as a vector from O to P with a left side jungle of GT simplex is present there, or with the right side jungle where all the entangled line segments are on the right side. We can think it in that way. And if we reverse the vector from P to O, then also there is a left side and there is a right side. So ultimately four symmetries are there. For a line segment, it is not a vector, because for a vector only one direction is taken care. But for line segment, we consider the start to end with the left side, start to end with the right side, and also end to start with the left side and end to start with the right side, which means the travel direction has a left side and also a right side, because the entangled line segments can form on the left hand side, entangled line segments can form on the right hand side of the line from its start point to end point. The start point to end point of any line segment is considered as the local x-axis, and when we do the 90-degree rotation, it becomes a local y-axis of that. In structural engineering or in any kind of triangulations for finite element analysis or for the network analysis, these kind of orientations are very important, because these orientations are carried into the chain complexes or in simplexes or in cochain complexes. Any kind of topological analysis of these kind of geometry, like Delaunay triangulations or Voronoi diagrams, or in protein folding, or in origami, or in bridge design, or in architectural structures, or in roadway planning, or in GPS networks, the direction of movement and the left side, direction of movement with the right side, the direction of movement reversed with the left side, the direction of movement reversed with the right side, all these four symmetries are very important to consider. Otherwise we cannot think deep into the topological properties, the neighborhood properties, the nearness properties. Connectability related issues are also there. The inquiries are more deeper in these kind of geometric arrangements. So we cannot get satisfied only with one kind of direction. So vector is a very small lightweight data structure if we consider it to handle with the topology data mining. To do the topology data mining or the point cloud data mining or on the line segment data mining or on machine learning or neural network data mining on the objects of triangulation or on the networks of graph-like structures, then we have to consider all of these things. Strictly speaking, the direction of movement with the left side, the direction of the movement with the right side, the reverse direction of the movement with its left side, and reverse direction of the movement with the right side, all of these four things are very important for the line segment. So line segment is a heavyweight data structure which is not like vector. Moreover, since we have to play with the closure, point is not the right thing to handle. Line segments are also not right thing to handle. Line segments are the part of a triangle. We will consider it as a null triangle or any edge of a triangle. And triangles are the most basic, most fundamental structural and functional unit of geometrifying trigonometry or geometrization of trigonometry. And these line segments are useful for plus and minus in maximum cases, but for multiplication and division, line segment cannot play the whole role. So for multiplication and division of the cases, a triangle is a mandatory fundamental structural and functional unit of geometrifying trigonometry or geometrization of trigonometry. So without a triangle is taken into the play, we cannot do multiplication or division, because due to multiplication, one common edge is glued and aligned and scaled to fit, and that is the common edge of gluing for two triangles, and that we have already explained in 2 or 3 videos in detail. But in one video we have dedicatedly explained the multiplication as gluing, where aligned and scaled to fit operation is explained. In another video in another 2 to 3 videos we have explained very well how divisions are taken care and how the divisions of two objects of geometrifying trigonometry generates a triangle, and every triangle has a initial line segment and a final line segment. Whatever are the things are generated for any given trigonometry expression, any kind of trigonometry expression look like these kind of things, or any larger kind of trigonometry expressions, whatever it is there, we will have to keep in mind that every part, like every component of any whole trigonometry expression can have basically two things. One thing is inside the trigonometry ratio, either it is 3 theta, 5 theta, or any big large expression is inside the trigonometry ratio, inside the bracket of the trigonometry ratio. We will take it as a pure number which is representing any angle. The angle object is an interesting object, but for that we will discuss in later videos. These angles are pure numbers with some internal properties, and with those properties there are several deep theorems also present, but we will talk about those things later on. Currently we will think about the two basic things, either the object which are the expression like things inside any trigonometry ratio, like cos, sin, tan, cosec, sec, cot. These are the trigonometry ratios, and within this trigonometry ratio there are the brackets, and within that bracket several small or large things can come there, but we will take all those things as pure number. And another thing is that whatever are made up of this trigonometry ratio, these things are all locked set kind of things. Either it is a GT simplex, GT simplex is a multiplicative kind of thing, or this kind of thing. These are the GT simplexes. The left hand side, these expressions are GT simplexes, like sin square theta, sin cube theta, sin 4 theta, or sin theta cos to the power 6 theta, or cos to the power 6 theta into sin to the power 15 theta. These kind of things are all GT simplexes where only multiplications are involved, and whenever plus or minus are involved, that is the locked set. Whenever any GT simplexes are added or subtracted, those are all non-commutative. All plus minus into divide in geometrifying trigonometry are non-commutative, and when these non-commutative objects are all made up of the line segments, and large number of line segments with different kind of symmetries are present there. But keep it in mind, the fundamental axiom of geometrifying trigonometry says that all of these GT simplexes are constructed from a single given line segment L, and these GT simplexes are added or subtracted in any order, and then that forms a locked set, and all these locked sets are inherently carrying that initial line segment that is common. When we move that initial line segment, the whole locked set moves together. All the things, all the entangled line segments will move together. Now we have already discussed in our previous videos that when we generate these kind of GT simplexes, every of these GT simplexes have a output line segment, and these output line segments are different. Obviously all of these are generated from the initial given line segment L, but all of these output line segments are different. When a locked set is divided with another locked set, then it forms a triangle which also have a initial line segment and the final output line segment. In the case of division, sometimes it happens that the denominator is not the same as the initial line segment, but that is also generated from that specific one single initial line segment L. So everything are connected with that initial line segment L, and we can tell it in a easy terminology that whatever we are constructing any geometrifying trigonometry construction, all of the constructions are done from a single seed initial line segment L, and we cannot escape from there. And all the line segments for all symmetries, all possible geometries, everything in the geometrifying trigonometry for a single trigonometry expression, all of these things are originated from a single given line segment L. So all of these entangled line segments are directly or indirectly, or sufficiently indirectly connected with and entangled with that initial line segment L. Now after division we can get a triangle, and those triangles, two triangles are similar, so there is a ratio which is similar, and in that way in our previous videos we have already explained about those things. Now in today's video we are trying to explain the natural summability of these kind of line segments. Suppose in these expressions where 3 minus 4 cos 2 theta plus cos 4 theta, or suppose in this log set 3 sin theta minus sin 3 theta, or suppose in this log sets where it is written as the 10 sin theta minus 5 sin 3 theta plus sin 5 theta, or suppose in this log set where 3 cos theta plus cos 3 theta. These kind of log sets are there. What it means when we see this kind of log set, suppose 3 cos theta plus cos 3 theta, we can write it as cos 3 theta plus 3 cos theta, but the geometry are different because the whole constructions are non-commutative. Now when the problem is non-commutative, the question comes is that everything are interacted with the final output line segments. Here the 3 cos theta is a line segment and cos 3 theta has output line segment. 3 cos theta is a GT simplex, cos 3 theta is a GT simplex, but all GT simplex have a final output line segment, and they are added, and when they are added the whole GT simplex are moved. So suppose when we are translating, rotating or scaling any kind of line segments, whatever we are doing, or if we are doing any mirroring of these line segments, the not only these output line segments are transformed, all of the entangled line segments which are connected with these output line segment, everything are transformed in the same way. So if a transformer T is used on output line segment, that same T is implemented on all of the entangled line segments which are there involved with these output line segments. And when this happen, when we use any transformation tau on these output line segment, in that case the initial line segment for this object is also transformed, and that is forming a copy of initial line segment. The original line segment is same, kept there, but the copy of original line segment also transforms, and it makes a copy on the whole system on the affine plane. Now suppose there is a red colored line, suppose L is the red colored line which is the initial line segment for the output, and when this tau operator is operated on this output line segment, that tau can be translation, rotation, scaling or flipping or mirroring or whatever, that or multiplication of multiple transformer are used on these output line segment. Then one copy of the initial line segment which is already entangled with this output line segment will also get transformed, but the original line segment is locked with other entangled line segments of these. So we cannot move the original initial line segment, but for this output case or for some other GT simplexes or for some other locked set, one copy of that initial line segment will get with the transformation tau, such that we can capture that also in the topology data mining, that where these initial line segments copy goes due to the transformation done on the output line segment. This is an important subject for geometrifying trigonometry, and these kind of copies are having different properties, and we try to do a data mining on these kind of copied initial line segments to identify that how much deviation is necessary to add two different line segments. There are several cases where we see that when we place the output line segments one after another, then no transformations are necessary on the initial line segment or on the output line segment. And when we can get this kind of contiguous outputs, like the output is generated from the given L line segment L, this output is generated from the given line segment L, and this output is generated due to the given line segment L, and if a translation is necessary, then obviously the copy of initial line segment is generated, because this entangled whole set is moving, and with that the initial line segment is also forming a copy when it is transformed like translated, its translation is also transformed. So it is a bad thing. That is not a good thing, because copying a initial line segment due to necessary transformation, making the whole meaning a bad meaning. The real natural summability is possible when we don't need to translate, when we don't need to rotate, when we don't need to do any flipping, and when all the outputs are generated one after another automatically. And if the outputs are generated in this way automatically, then we can consider that it is a summability. And if all these are naturally linear, if all these outputs are naturally linear, then it is a natural summability, the best natural summability. If all the output line segments are collinear and end to end, then that is best. Otherwise, this kind of cumulative summation is also good. And sometimes we can do the juxtaposition of these terms to get this kind of output. And if all of these are naturally forming from the initial line segment L without moving, without transforming the initial line segment, or without making any copy of initial line segment, then these kind of outputs, where the contiguous output line segments are forming, that is the best option to get a natural summability. And if that is a collinear, then that is the best natural summability. These kind of things are very interesting subjects. Suppose here with these images we can say that 1 into cos theta and 1 into sin theta into this one is cot theta, 1 into sin theta into cot theta and cos theta, they are naturally collinear, forming 2 cos theta, because we don't have to change this one, we don't have to make any copy of this one to get this output line segment. And since we don't need to get this line segment collinear by forcing the movement of one, then these are naturally summable. And this is cos theta, this line segment is 1 into sin theta, and this line segment is now the base of the triangle, where this is not the base of the triangle, this is the perpendicular of this triangle also. And when it is the perpendicular of this triangle, and perpendicular is known as the 1 sin theta, and we have to find the base, then perpendicular is in the bottom, in the denominator, and base is in the numerator. So base by perpendicular is the cot theta. So that means 1 into sin theta is known, this 1 into sin theta is multiplied with cot theta to get cos theta, and this cos theta line segment is also collinear with the initial cos theta here, and these are naturally collinear. So we don't have to move this one, nor we have to scale this one, nor we have to rotate this one, nor we have to do any flipping on this one. Naturally we are getting this output line segment cos theta naturally collinear with the initial cos theta. So in the glued form of this common line segment, we are getting a natural addition of this cos theta, and this natural addition is 2 cos theta, where if we get this theta here, then 2 cos theta is the length of this whole line segment. This into sin theta is getting into 2 cos theta into sin theta is this one, and that is the 1 into sin 2 theta. These two are naturally equal in length and naturally parallel, and these natural parallel conditions are giving us interesting property here. And this kind of formation is man-made, but geometrifying trigonometry and geometrization of trigonometry can generate very large number of pictures. And there is a theorem which says when 2 cos square theta is there, that means it can generate 16 pictures of this symmetry. which is a very interesting theorem, because 4 into 4, for every multiplication 4 times it is done, because plus is of 4 types, minus is of 4 types, into is of 4 types, division is of 4 types. We can do this whole thing flipped and we can get a cos theta, and in that case a natural flipping is forced flipping is done, and so we cannot say that is a natural summable condition. It is a forced summable condition, because the initial line segment has to tweak. We have to change the initial line segment's position, original position, and that consumes a lot of energy, and so minimum energy principle is not fulfilled. The minimum energy principle fulfills when we don't have to move the initial line segment anyhow, and naturally the line segments which are generated in the output are contiguous, or best when they are naturally collinear. We were trying to say the permutation, every different permutation are giving the valid output picture, but which juxtaposition gives us the minimum energy natural summability condition is to find, and there are so large number of pictures forms due to these kind of expressions, because there are large number of powers are there. For every multiplication 4 times pictures are forming, like for sine cube theta there are 64 pictures, for sine to the 4 theta 4 into 4 into 4 into 4 there are 16 into 16, that is 256 type of pictures will form on the left hand side. And now out of all these 256 types of pictures, the output line segments are also 256. Now we cannot assume that all these 256 output line segments will give us the best result, and since in axioms of geometrifying trigonometry is saying that cos theta are of 4 types: A symmetry, B symmetry, C symmetry, D symmetry. Sin theta are of 4 types of symmetries: E symmetry, F symmetry, G symmetry, H symmetry. Tan theta have 4 symmetries like I symmetry, J symmetry, K symmetry, and M symmetry. Sec theta has 4 types of symmetries: N symmetry, O symmetry, P symmetry, Q symmetry. And cosec theta has 4 symmetries: R symmetry, S symmetry, T symmetry, U symmetry. And cot theta has 4 symmetries: V symmetry, W symmetry, X symmetry, and Y symmetry. And L is the initial line segment and Z is the final output line segment forming due to the whole process. And so all the English alphabets in capital letters are used up in the 26 symmetry, 26 kind of line segments are initially defined, and then we have the other axioms where triangle constructions are anti-clockwise, clockwise, or in another axioms of geometrifying trigonometry or the geometrization of trigonometry, it is saying that the pivot point to stretch point is mandatory. All other line segments can take any orientation. In another axiom it says that stretch to nodal is mandatory, that is direction is mandatory, and other 2 segments can take any of the position, any of the direction. And in another axiom it says that pivot to nodal is mandatory and other 2 line segments can take any other directions. In that way several minimum energy principles choosers are designed, and out of these designed conditions every symmetry has a unique specified well-defined names, like the points are also having well-defined names: the pivot point, stretch point, and nodal point. Those are all well nomenclature done to get the canonically axiomatic formalization such that the computability conditions cannot get any ambiguity. Any theory should have a non-ambiguous situation. The theory should have the axioms tight enough such that no paradox can occur while doing the constructions or while writing the programs. And we have already made the simulator. Sanjoy has already made the simulator for this, and while designing the simulator for the outputs construction, Sanjoy found that these kind of nomenclatures are very necessary, otherwise there could become the chances of ambiguity, or there could become the chances for the paradoxes, or several kind of fallacies could occur, or runtime errors could occur. So whatever the kind of errors there could happen, all of these things are nullified through the rigidly, tightly, well-defined terminologies, and the construction protocols are designed. And while doing the data mining, we needed some measures to calculate the minimum energy principles, to find the least work conditions such that we can decide which juxtaposition of the outputs is the best possible output to write the expressions in identity. Suppose 3 sin theta minus sin 3 theta is one thing, and for this expression like 3 minus 4 cos 2 theta plus cos 4 theta can be written as the 3 plus cos 4 theta minus 4 cos 2 theta, but are both giving the same kind of best arrangement of the output line segment. Sometimes it will give the same output whatever juxtaposition we do, sometimes it will not give the same output, and so some rigidly defined, well-defined principles for constructibility should be there, otherwise the ambiguities can occur, otherwise some paradoxes can occur. So to avoid all these such conditions of constructibility, Sanjoy had to define the axioms very tightly such that the juxtapositions of the permuted objects are calculable such that we can get some right information, right decision conditions such that we can choose the right way to write the expressions to meaningfully represent that the best arrangements, best smooth curvatures or best collinearity are achieved through the output line segments. And that is the purpose of geometrifying trigonometry, to find the minimum energy principles conditions where the natural pictures which are forming due to the computable algorithms, we can decide many deep theorems such that we can auto construct these kind of pictures from any kind of geometrifying any kind of trigonometry expression. That is the fundamental purpose of geometrifying trigonometry. And after these kind of expressions are generating pictures and several large symmetries of the pictures, we can do deep inquiries. Like suppose in this picture you can see, suppose in this picture we can see, suppose there are thousands of such line segments are forming there, we can inquire the TensorFlow or PyTorch that within this learned set, search me the possible combinations where good rectangles and congruent rectangles are forming, and it will give us the outputs where it will say that this one is a one line segment, this one is a copy of L, the copy of L sine 2 theta and another copy of L sine 2 theta with the 2 cos theta into cos theta, that gives the 2 cos square theta, which is this long line segment, minus cos 2 theta. These 4 line segments are forming a rectangle. In the other symmetric pictures, some other line segments will forming a rectangle and both can become congruent. Till now in this picture we are not seeing those things. Suppose we are trying to get the inquiries where which of the points are getting the same circle, which of these points are coming on the same circle, and without constructing this kind of picture, our data mining system can generate these kind of theorems, and from the TensorFlow we can search these kind of pictures and also generating the theorems out of the large number of set of line segment data or large number of set of triangulated triangulation data. We can conclude these kind of deep theorems, and which behaves as the invariants in the geometrifying trigonometry, where for theta varying from 0 to 360 degree, everywhere these properties hold. These invariants are very deep kind of topological data mining things, which kind of theorems we have never seen in trigonometry previously. Until we can construct this kind of all symmetries, the exhaustive list of all pictures, until we can construct all those things, we cannot expect that we will get these kind of insights. Until these pictures are constructed, auto constructed, we cannot get the insights of the arrangements of line segments or the shapes hidden inside these kind of symmetries. Those kind of deep understanding is not possible. So geometrifying trigonometry is going to give us a better understanding on the protein folding mechanisms, on the linkage mechanism designs, on the mechanical moving parts designing, or in the bridge designing, or automated positioning of the free body diagrams, for where we will put the objects in such a way that the minimum energy principles will work. These kind of new emerging subjects will come up with the theorems of geometrifying trigonometry, and it is vast because sometimes we can see that there are millions of line segment data, and out of that we will have to find several patterns, and from those patterns we will find some deep links between the different kind of shapes forming due to the output line segments juxtaposition. You have seen that several of these output line segments juxtaposition, all of which are entangled with the initial line segment, and still they are forming some beautiful pictures. Sometimes it will form some fractal like pictures, sometimes the fractals of the different symmetries will form but the perimeters will remain same. In that case the isoperimetric optimization problems are also possible. Sometimes we will find that there are large number of curves forming, all are having the same total length, but they are looking entirely different. If you look in the geometrifying trigonometry and if you search in Google, you will see large number of sample pictures that Nath has already uploaded in Quora or in GitHub or in YouTube videos, where you will see several isoperimetric curves are there, where the curves looking very different but they are all having the same expression, and all of the integrals of these quadratures are giving the same output but they are entirely looking different. And some of these curves are discontinuous, some of these curves are smooth, but all of have the same integral values, and these are going to give us the newer insights on the calculus, and in that way we can get the deeper analyzability with the geometrifying trigonometry, which we were not getting till now. Until geometrifying trigonometry was there, we were not about expected that someday we will get this kind of topological possible inquiries on to be done on the trigonometry expressions. Thank you.